Welcome, everyone. Thank you for joining us for today's webinar. My name is Jennifer McKay. I'm the Policy Director for Tip of the Mitt Watershed Council and will serve as the moderator for today's webinar. And today we are presenting Climate Change Adaptation, Best Management Practices for Coastal Wetlands in Michigan. We have a great panel of experts for you today, including Richard Rood, Dr. Donald Uzarski, Ralph Reznick, and Ann Garwood. Just to let everyone know, today's webinar and the best management practices were developed in part through a Michigan Office of the Great Lakes Coastal Zone Management Program grant. Funds were provided by NOAA through a state and federal partnership established under the Coastal Zone Management Act of 1972. In addition, we also developed a publication, and the Climate Change Adaptation, a toolkit of best management practices for coastal wetlands in Michigan, is available for download. It's under the handouts section on your right-hand panel. It's also available on Tip of the Mitt Watershed Council's website, www.watershedcouncil.org. Or if you'd like hard copies, feel free to contact me directly, and my email is currently up on the screen. Quick little housekeeping before we get started. You have the opportunity to submit questions to today's presenters by typing your questions into the questions chat pane of the control panel on the right side of your screen. You can send in your questions at any time during the presentations. We have a full schedule, so we'll ask 1 or 2 questions immediately following each presentation, but we'll be collecting all of the other questions to be addressed at the end of today's webinar. If you experience any problems or technical difficulties, please notify us using the chat box. We have staff monitoring it and hopefully can get the problem fixed quickly. So without further ado, we're going to turn it over to our first presenter, which is Richard Rood. He's a professor in the Department of Atmospheric, Oceanic, and Space Sciences in the School of Natural Resources and Environment at the University of Michigan. He teaches atmospheric science and climate change problem solving. He has made research contributions in the field of numerical modeling, data assimilation, and atmospheric transport and chemistry. He also has experience in the design, implementation, and management of software and hardware systems used in high-performance computing. In 2006, Rood initiated a cross-discipline graduate course, Climate Change, the Move to Action, which explores problem solving in climate change and motivates his current research interests. The primary focus of this research is to accelerate the use of knowledge from science-based investigation of the Earth's climate in planning and policy.
So this is Ricky. Can you hear me?
We can hear you, yes, thank you.
And you can see my screen?
Yes.
Okay, excellent. I will try not to make my desk squeak, things like that. So what I was asked to do today was to give a general overview of climate change in the Great Lakes region, and that is what I am going to attempt to do really rather quickly. I'm not going to really talk about impacts that much, and in the website that I should have on what will be my last graph, there's a link to GLESA, and GLESA you see right here, which is the Great Lakes Integrated Sciences and Assessment Center, which is a partnership between Michigan State and the University of Michigan. A longer version of this presentation is on that website, as well as many other resources. So just to begin, I click the button. There you go. You've probably seen pictures like this, and what's shown here is from 1900 to 2000. This sort of shaded line here is variability, and this dark line here in the middle is actually model sort of representations of the last century, and this variability here, I think in this figure, is actually sort of observational variability. And you can see that for the last 100 years, there's been this temperature increase, which is about 0.85 degrees centigrade from 1880 to 2012. 2013, 2014, 2015, 2016 have all actually been warmer, so this trend is becoming more robust and accelerating. The models do an okay job, really quite a good job of representing this variability. And then going forward, what you see is this sort of continued warming. And what these different colors are sort of different versions of what emissions and land use change will be like, where this red one, the 8.5, and these numbers, these are a little different than the scenarios that we used to use. This is sort of limiting to a certain amount of radiative forcing. This one is really closer to the path we're on than anything right now. And these are reduced emission scenarios and the like. You can see that there's a rather strong indication of continued warming. This sort of lowest emissions is almost sort of comparable to if you just turned off things today. If you just turned off all carbon dioxide emissions today, the planet would keep warming. So we're in a situation in the global mean where it has warmed, it is continuing to warm, and it will continue to warm over the next many decades and probably several centuries, ultimately depending upon what we do in the next few years in terms of mitigation of climate change. So adaptation is in our future. So global trends are really quite certain at this point. But when you get to regional and local scales, sort of the impact that climate change has on weather becomes important. And with the planet warming, with sort of the additional water that ends up in the atmosphere due to increased evaporation from the oceans and the lakes, due to that warming, the weather pretty much has to change. There's no way that you can add additional energy to the system in that way and expect the system, say, to remain stable and to not respond. And so as the scales get smaller, this variability associated with weather plays a larger role. And also local changes in land use practice can have strong roles. There are some places where there have been trends, but those trends are actually due to, say, changes in agricultural practices. And there are parts of the Midwest, especially down in sort of Illinois, Indiana, Iowa, where irrigation plays such a large role that it actually perhaps obscures even some of the climate change signals. I meant to take this slide out and thought I had, but I'll explain it since it's here. One of the ways that people sort of think about this is for Michigan or for any of the states up in here, is to think that, you know, here in 50 years, you're going to have temperatures that are more like what you see down through this geographical region. And in 100 years, you're going to have temperatures that are more like here in Oklahoma and Kansas. I normally don't use this plot because I think it gives something of a false impression of what's going to be happening with water and the like. Plus, there's some interesting messages here where this idea, many people in the Great Lakes, when they see this and they see the climate of Kentucky, they actually view that as a good thing. And and in some cases, you know, it might be, but that's sort of whitewashing on some of the broader issues of climate change. So what's changed? I think it's important to look what has already changed. And temperature and precipitation have changed. The averages have changed, the extremes have changed, and the seasonality have already changed. These changes are all consistent with a warming climate. They're all consistent with the guidance that's coming from climate models. And for the most part, we anticipate that these changes will continue into the future with sort of the same sign that we are already seeing. So what I want to do here is just briefly go through some of those changes. So this is a picture which is using climate divisional data, and that's just a geographical extent of climate for 8 U.S. Great Lakes states. And it shows sort of the variability here with a 9-year running mean. And sorry about the cough. What you see, and this is sort of consistent with global picture, is that since 1980, the start of this really quite definitive trend upwards. And if you go back and look at those models and do attribution studies, really the only explanation for this upward trend is related to increasing carbon dioxide. So regionally, we can go on and see this. If you look at projections already with the very high emission scenarios between 2070 and 2099, these sorts of, and here we've gone back to scenarios that were used 5 years ago, which are directly related to carbon dioxide emissions. You see, you know, these numbers here in Fahrenheit up around 14 degrees or so, and a low emission scenario is 4 to 7 degrees. Note sort of that regionality issue. These numbers are quite a bit bigger than that global average. We're also seeing these sort of persistent patterns of heat waves where we have extended periods of heat, which can have big health effects. But I think what I'll point out here, some of the bigger trends are in overnight minimum temperatures that are increasing at faster rates, and this, you know, impacts environmental cooling as well as agriculture and ecosystems. And we're moving towards this increase in the number of hot days. And, you know, again, this is sort of interesting in the fact that down here, you know, up in the Mississippi Valley around St. Louis, these numbers are very high, and that sort of obscures this. But even in the Upper Peninsula, you're seeing the potential here of increased numbers of sort of hot spells. Longer frost-free season, length of the growing season is increasing, viewed by many, again, as a potential advantage. You see this west to east gradient, but you're looking at 9 days up towards 2 weeks, and this is already observed. Again, this is observed here. This is not something from a model projection. And then the lakes themselves are just a very interesting attribute, is that Lake Superior right now is warming twice as fast as the nearby air. Winter ice cover is decreasing. And this is a little bit counterintuitive because, you know, water is harder to change than air, but is likely related to changes in circulation and seasonal patterns. So again, quickly, precipitation, looking here, has already gone up by about 11%, and again, much of that change is since 1980. And then this is a chart that has attracted a lot of attention. This is the amount of precipitation that is occurring in extreme events, such as caused the flood, say, up here in Duluth. And since 1958, the amount of precipitation that occurs in these extreme events, which we mean the heaviest 1%, has increased by 37% in this region. Nearly doubled up here in New England. And this precipitation is coming in different seasons. There's more precipitation falling as rain instead of snow. The warmer surface temperatures have reduced snow accumulation. And then there's this interesting, again, almost counterintuitive aspect that because the lakes are warmer and open, there's been more lake effect precipitation so that you actually see greater snowfall, say up here in the Upper Peninsula, and greater snowfall here, greater snowfall down here. But it doesn't stay. And this is because of the warming lakes. There's less snow down here. So these are pretty dramatic changes in water availability and runoff, and have consequences for ecosystems as well as agricultural and human systems. Again, looking at projected snowfall days, we're actually generally expecting this to go down, such that, say, Minnesota, Wisconsin, and Michigan, the average number of snow days per year is expected to go down by more than 50%. And I think that I will sort of not go through these sort of scenarios and the like looking into the future, with the exception of pointing out there are some seasonal aspects to this, but for the most part, we're expecting more precipitation, especially in the fall, less in the spring, in the summer. So again, we're getting sort of runoff and change issues. And again, these are consistent with what we're already observing. And at this point, I'm just going to say I picked up the wrong presentation off of my computer, and I am going to the last one here and just say these materials and a whole lot more are at the GLESA website, which you can get at glesa.msu or glesa.umich. And I think with that, I will conclude.
Thank you, Ricky. As a reminder, please be sure to type any questions into the question box in your GoToWebinar control panel. At this time, we don't have any questions, so we're going to move on to our next presenter, Dr. Don Uzarski. Dr. Uzarski earned dual PhDs in 1999 from Michigan State University. Since that time, he secured over $25 million in external funding as the lead principal investigator and has published more than 60 peer-reviewed scientific manuscripts. He's received a highly cited author award from the International Journal of Great Lakes Research, and to date, his research has been cited in over 180 scientific publications worldwide. So we'll hand it over to you, Don.
Okay, thank you. Can you hear me?
Yes.
And can you see my screen? No, you can't, not yet. How about now?
Yes, we can. Thank you.
Okay, so I was asked to talk about Great Lakes coastal wetlands in general, talk a little bit about how the impacts of climate change will address these systems, and in particular through water level change. And then I'm going to briefly talk about our 10-year, $20 million coastal wetland monitoring program that we have ongoing. Right now, you're looking at coastal wetlands of the Great Lakes, and this is not every single Great Lakes coastal wetland in the basin, but it is every single Great Lakes coastal wetland that is at least 4 hectares in size with a surface water connection to the Great Lake. And these are just color-coded based on the wetland type. So we sample, you're looking at 1,039 coastal wetlands. We sample over 1,000 every 5 years. 70% of these are found in the United States, and of those 73% are in Michigan. We've lost by acreage over 50% of the coastal wetlands basin-wide, and in some areas like this, you're looking at Saginaw Bay, we've lost 95% of coastal wetlands to date. And everything in red along the shoreline right here are coastal wetlands that are already lost, and in turquoise, you see those that remain. I generally break down coastal wetlands into 4 coarse coastal wetland types, from open embayments with a very dynamic hydrology to protected embayments, barrier beaches where a sand spit forms and cuts off a embayment from the Great Lake itself and forms a wetland behind it, and then drowned river mouth systems. These systems are structured based on wave energy and hydrology is absolutely everything to these systems. Where these open embayments have very dynamic hydrology, you can not uncommon have 4 or 5 foot waves coming through the wetland. On the other end of the continuum, we have the riverine sites or the drowned river mouths with little to no wave energy. This wave energy and hydrology structures the ecosystem, so it's going to determine what type of vegetation we're going to find dominating in the ecosystem. For example, in the open embayments, we can have areas that are nothing but bulrush because bulrush can withstand very large waves. On the other end of the continuum, cattails are very good competitors under high nutrient conditions and benign hydrology like we find in these riverine wetlands. Also nutrients. If nutrients enter this system, they're going to be quickly diluted or flushed away. And on the other hand, in these drowned river mouths, nutrients are coming off the landscape and very much accumulating in the wetland itself. And that goes along with the accumulation of organic sediments. So we're going to have a lot of organic sediments here. We may have a cobble rocky bottom in this wetland over here. The organic sediments are going to control oxygen fluctuations that we would expect to see in the wetland on a daily basis. The open embayment, we would expect oxygen to be maintained at or near 100% saturation on a diel or daily basis. On the other hand, in the drowned river mouth, we're going to expect oxygen to plummet at night. Even anaerobic conditions, no oxygen in the wetland itself. But during the day, these very productive systems can go up to 180% saturation of dissolved oxygen in the water. So let's focus on just these fringing type wetlands, and they're called fringing because it's vegetation around the shoreline of an embayment, and then it's open water, directly to the open water of the Great Lakes. And we can ask the question of what makes the fringing coastal wetland so unique. And I like to use the example or compare it to an inland depressional wetland, or what we would call a palustrine wetland or a pond-like wetland that you might dig in your backyard. If you dig a wetland or a pond in your backyard, in a couple years from the seed bank, it's going to look something like this. You're going to have submersed aquatic vegetation in the open water habitat, floating leaf vegetation around the edge, but through time, we're going to have nutrients and sediment beginning to fill this system in. And this is a natural process, but humans tend to speed it up very much so. So as the pond is filling in, we then reach this intermediate depth where this emergent vegetation, in this example I have cattails. Cattails will start to take over your pond. And at this point you have an emergent marsh or a cattail marsh. If we don't dig it out and continue to wait, we get sort of a drastic change in that now very shallow water habitat is isolated to the center, and grasses and sedges will dominate the system. And at this point, our our cattail marsh turned into a wet meadow dominated by grasses and sedges. Essentially, it is too dry for cattails to win competitively and too wet for the woody vegetation to encroach on the system. But again, through time, it'll continue to fill in, and then when we have 1/3 or less of the growing season inundating this system with water, then woody vegetation will come in. Now the system is turned from a wet meadow to a swamp, and in this case, a shrub swamp. And if we wait long enough, we'll end up with a forested swamp. So essentially, we've gone from this backyard pond type environment to a forested swamp, and if we waited long enough, this would be upland. So we can look at it in a different way. If evaporation, for example, from climate change increases in this pond-like environment to decrease the duration of deep water inundation, it's going to turn into a cattail marsh. And if that evaporation increases even more without replacement of the water, the cattail marsh becomes thicker, and then we see that drastic change as duration of inundation decreases, to where now grasses and sedges outcompete the cattails because the system is now too dry for the cattails, too wet for the shrubs. But if the system does continue to change, we'll have shrubs moving in, the shrubs will thicken, and if the duration of inundation decreases anymore, we're going to have a forested swamp and eventually upland. So again, we've gone from that pond-like environment to a forested swamp. Well, now we're looking at the profile of one of those fringing Great Lakes coastal wetlands. And we see very distinct zonation in these systems. And that zonation in the coastal wetland is essentially the spatial equivalent of succession in time, in that we have each component of our backyard pond structured as we move from open water of the Great Lakes on this side. We have that aquatic bed, pond-like environment. Then we move into our bulrush marsh, our cattail marsh, our wet meadow, and finally our shrub swamp and forested swamp. So at one point in time in a coastal wetland, we have all of these different wetland types that we would find through succession of an inland wetland. Along with that, we have that dynamic hydrology where the outer portion is very much wave swept, and you can imagine that the chemistry of this outer portion of the wetland is very similar to the chemistry of the Great Lakes open water. On the other end, we have almost no wave energy because of the vegetation blocking and dampening the waves, but instead we have groundwater component coming into the system, so we have a very different chemistry on this side of the wetland. And we can kind of visualize that if we're looking down at a coastal wetland, and this is upland, this green portion is the wetland itself, and the top portion is the open water of the Great Lakes. The water from the open water, the pelagic zone, gets forced into the wetland, and it's indicated here as red chemistry, and there's no meaning to that red. It's just the color I'm using here. And that chemistry changes as that water is advected across those organic sediments. And from the other direction, we have a very different chemical physical characteristic of the water coming in from groundwater, and that changes along through the wetland as well, setting up this very distinct chemical and physical gradient from open water to inland. And then the biota, or the organisms, can pretty much find their optimum, find their best chemical conditions and physical habitat. And we get a very dynamic ecosystem and diverse ecosystem. We can see this zonation from satellite figures or even aerial photos, in that this portion is the wet meadow that I just talked about. We have a narrow band of dense cattails, transitions into a dense bulrush zone, and then finally a very sparse bulrush zone, and again, very different chemical physical conditions as we move along this axis. And you can see that. So now we're at Saginaw Bay, and I'm standing on shore, basically with my feet in the water, and we're looking out here. This is the other side of the bay, but we're looking out here at open water, and you can't even see it because we have 300 to 400 meters of bulrush here. You can imagine that the chemistry at my feet is very different than if we're in a boat now looking back towards shore. And you can see this wave energy and this wave action setting up that very different chemistry. Well, over the past 15 or so years, we've seen some pretty drastic changes in water levels. And you're looking at mud right here in this marina. Essentially what we've seen, 1997 was a high water year, and water levels came down, and water levels, you're looking at Lake Huron, Michigan right now, and they fluctuate up and down like they should, but for a 15-year period, they stayed below this long-term average for Lakes Huron, Michigan. And for a coastal wetland, that's not necessarily a good thing. This fluctuation that we see is very, very much a good thing for coastal wetlands and very, very much necessary. But I don't like to see water levels below the long-term average for more than 4 or 5 years at a time, just as I don't like to see them above the average for more than 4 or 5 years at a time. They should be fluctuating up and down around that. And we've seen an increase in evaporation from the lakes over the past 30 years. Again, it goes up and down trend, but the trend line is increasing in evaporation without the replacement. There are some potentially good things that you could look at it that way. Nothing from climate change is a good thing, but what is happening now, what used to be the coastal wetland in this region is filled, and we've built hotels and homes along the shoreline because we want to be close to the water. With this very long, prolonged low water level, coastal wetlands were starting to come back in regions, essentially migrating lakeward, where the coastal wetland would have been under this building. Now it's forming in front of it. However, that tends to trigger anthropogenic or human disturbance in these ecosystems. So this is a couple years later. We tend to want to fight the change in water levels. As these coastal wetlands over this time period decreased, we saw mowing, we saw tilling of the coastal wetland. You can see right here with low water levels, we try to get our beach back by tilling under the coastal wetland that's forming there. And it's interesting, we don't like the high water levels either. So you see this armored shoreline or this seawall to stop, again, the water from coming up. From 1997, we saw that drastic decline in water levels. We saw it plummet about a meter in a very short period of time. And we can go back to 1988 for an example. 1988 was following a very low drop in water. And essentially what was left behind was a mud flat in our coastal wetland because the water moved out to here. Now keep these trees for a reference point. 1 year later, the coastal wetland migrated like it's supposed to. So it migrated lakeward, and when water levels come up, it will migrate landward unless there's an armored shore or a building or a road that it can't migrate through. And this up and down of water levels is very good for the wetland. It actually increases the size of the wetland, the zonation of the wetland, and the number of zones that we find. However, now we're dealing with something else, and that's invasive species. So at this point, there are so many invasive species across the basin. When this mud flat or this prime real estate is left behind, the invaders can quickly colonize that, and that's what that system looks like today with this invasive Phragmites. So we're seeing this climate change invasive species interaction throughout the basin. Here we're looking at, in the mid-1990s, back to Saginaw Bay, and we're looking at our 300 or 400 meters of bulrush out to the open water. This is the mid-1990s. From this same location in 2012, this is what it looks like. Now the edge of the water is right here, and we're looking at 300 or 400 meters of Phragmites with a very narrow band of bulrush left behind. So that Phragmites is actually increasing sedimentation rate, which increases the elevation of this marsh. The ground is actually building up. And even like now, when water levels come back up, the water level doesn't make it all the way back up to where it used to on shore because this is higher ground. So we've essentially lost fish habitat and other aquatic habitat. But again, not all of this can be or should be viewed as being completely negative. And the example of Saginaw Bay with the prolonged low water levels, we saw invasive Phragmites spread to about 300 meters of the wetland. Of course, that's poor fish and wildlife habitat, decreases recreational opportunities, and increases that sedimentation rate in the wetland. However, that 300 meters of Phragmites is an excellent filter. Essentially, we're looking at from water now back through this wall of Phragmites, and you can just barely see the top of a tree on the shoreline there. Toxicants and nutrient pollution coming off the landscape does not easily penetrate through this tremendous filter. So it's important to remember now we've seen in Saginaw Bay and other places increase in water quality because of this filter that is established. So it's important to remember that even though it's a monodominant stand of Phragmites, it still has functions and values. And in this case, that one function of filtering capacity actually increases. So now I'll quickly switch gears and wrap up and talk about the Great Lakes Coastal Wetland Monitoring Program. In 2010, we received a $10 million grant from Great Lakes National Program Office, the US EPA, that covered the period 2010 to 2015. In 2015, we received another $10 million to continue through 2020. And essentially what we're doing is measuring ecosystem health at every single coastal wetland, US and Canada, that is greater than 4 hectares in size with a surface water connection to the Great Lakes. At each of those sites, we sample every component of the ecosystem, chemistry, invertebrates, fish, plants, birds, amphibians, and we have a sister project that does adjacent land use land cover to each of these wetlands. These are some of the data. This is just chemistry data from 2015 looking at water quality. And essentially what it shows, something interesting here, and I pull out a site in particular, where 2012 was a low water year and the water levels are coming up and so is the water quality. And then there are other cases where I can show you that a given wetland has differing water quality based on what zone you're in. So one zone in this wetland has moderately impacted water quality. Another zone has reference conditions or the best you could expect. By the way, red is bad, green is good here in this figure. This is vegetation data, so these are plant data only telling us about ecosystem disturbance. And it tells us something on a very coarse basin-wide scale in that where you find the people in the southern lakes, you tend to have lowest quality, and in the upper lakes, you have good quality. That should be no surprise to anyone. But we can use our other data like the aquatic macroinvertebrates, or think of this as fish food, to get fine scale resolution on human disturbance and impacts to the ecosystem. For example, in this region, you can see we have a degraded site, about the worst we can expect, right next to one that is in pretty good shape. And then the fish data can tell us something different because fish are relatively mobile. So now you can tell there's a scale somewhere between that basin scale and the very fine scale indicating human disturbance. And then we can relate back to particular disturbances. So anyone can access the database. There's an enormous amount of data here. We have different levels of access, and that EPA and our project researchers, of course, can access the full raw data with manipulation capabilities. State and federal wetland managers can access some of the raw data and all of the analyzed data. Non-governmental organizations working on restoration and conservation can access analyzed data, but on a case-by-case raw data as well. And then the general public sees very summarized data from the wetlands. To get to the website, you can go to the Central Michigan University Institute for Great Lakes Research website. Just Google that. Over on the right-hand side, click on Great Lakes Coastal Wetland Data. It'll take you to the front page of the database. You can click on the mapping tool, and these are all of the sites that we sampled. You can click on one individual site. It'll give you our reference number, the name of the site, the location of the site. And then you can zoom into a region of interest. You can actually zoom down and look at the actual polygons of the coastal wetlands themselves. Switch that, if you like, to a Google Maps or Google Earth type view. click on that, again, you're going to get the name, the location, and then the data behind that map. Our project is very large. We represent 10 universities and 3 government agencies that are key in this work across the entire basin. And of course, the US EPA is not only our sponsor, but also our partner on this project, and they're very much involved in the day-to-day work. And with that, if I have time, I'll take questions. If not, we can move on.
Okay, we did have a number of questions coming in. We may only do 1 or 2 given the interest of time. And the first one is, will the wetlands that have been lost in the Saginaw Bay area come back with the water movement that you've shown?
Well, yeah, and we did see that through over the low water level period. You know, you'll see a seawall where high water level was tried to stop, but yeah, as the water moves away from the development, coastal wetlands start to restore, but we do have legislature that allows for at least some manipulation of the vegetation and removal of the vegetation or the wetland itself currently.
All right, and then what is the significant cause for coastal wetlands disappearing?
It's development, generally draining. You know, much of the Saginaw Bay area that I showed you that was in red is actually currently being farmed in its excellent farming habitat because it was wetland, and it's below Lake Huron water level. So we have dikes and pumps to maintain those fields dry so we can farm those, and development as well. So filling and we want to live on the water. We want to have our hotels, our houses on the water. So wetlands are almost dry and dry some of the years. So it's not difficult from an engineering standpoint to fill these and build on them. Well,
thank you, Don. And now, last but not least, we have Ralph Reznick and Ann Garwood from the Michigan Department of Environmental Quality. Ralph has worked for the state of Michigan in the DNR, DEQ, DNRE for 36 years in water quality protection. For the last 25 years, he has been the senior engineer for Michigan's Nonpoint source program with responsibility for developing and reviewing best management practice design criteria, including green infrastructure techniques and river restoration techniques. His bachelor's degree in environmental engineering from Oakland University in Rochester, Michigan, and is a trustee of the Village Council for Diamondale. Ann Garwood is the Great Lakes Coastal Wetlands Ecologist with the Water Resources Division in Michigan Department of Environmental Quality and works on wetland monitoring, invasive species, climate change adaptation, and protection of coastal wetlands. Ann's a member of the Aquatic Invasive Species Core Team in Michigan and on the board of the Michigan Wetlands Association. Ann has worked in the regulatory wetland program for several years in Southeast Michigan prior to accepting the coastal wetland ecologist position in 2010. We'll turn it over to you both.
Great, thank you very much. Let's see here. Can you guys see my screen all right?
Yes, we can, thank you.
Okay, great. So I'm going to start us out just talking a little bit about DEQ's involvement in adaptation of coastal wetlands for climate change. We have been working with the Coastal Zone Management Program for several years now to work with partners to develop best management practices for adaptation of coastal wetlands. And in particular, we're trying to encourage best management practices that people can do at all different scales. So this project that this webinar is part of is part of a partnership with Tip of the Mitt, where they developed this best management practices manual, the toolkit, that we're going to talk about some of the BMPs in that today. Previously, there was some work with Leah, who developed a guide for adaptation for local planners, basically recommendations for local communities to incorporate climate change adaptation measures for wetlands into their long-term master plans and things like that. And then there was a project a couple years ago with the Great Lakes Commission to develop some BMPs, and what they did were case studies, which included a lot of case studies on sort of planning efforts as well as some on-the-ground practices. So this is a long time coming, and we are excited to roll out all of these things and try and encourage people to start thinking about adaptation on their property and on their projects. What are some of the best management practices we're talking about and we're encouraging? Under sort of the overall category of preservation and protection, there are a lot of actions that people can do that they might not realize are climate change adaptation measures, in particular wetland and floodplain ordinances on a local scale. These are basically local ordinances which protect these natural features in a different way or sort of in addition to what might be state or federal protection. Protecting these local wetland resources is an adaptation measure because these wetlands do provide functions and values that will help in future climate scenarios. They help with flood storage, with nutrient management, with sediment runoff, with habitat corridors. These are really important, in particular with the unpredictable flashiness of storm events we're anticipating. We're potentially going to have longer droughts and more large storm events, so these wetlands are really important, as well as floodplain wetlands especially. Some other ways that wetlands can be protected are conservation easements can be placed over these wetlands. That's a great adaptation tool that local or individual people can use. And then some areas have setback requirements. These are especially important because they allow the wetlands to adapt and change over time. With the different climate scenarios that could happen in Michigan, we do anticipate that the boundary of these wetlands could be shifting. They could expand, they could contract. Different wetlands have different hydrology sources and different connections to other surface water bodies. So there probably will be changes over time in the shape and size of these areas, and setbacks allow for that to continue happening. They also provide a natural buffer to these areas, which can also significantly improve the quality of them and the functions that they provide. Whoop. All right. So another example of protection that could be utilized is one example would be prioritizing preservation of peat-dominated wetlands in order to protect those major carbon stores. In Michigan, we do have a lot of peat-dominated wetlands, and they are major carbon stores that, if they are developed or burned or the peat is extracted, can release significant amounts of carbon into the atmosphere. And protecting those and preventing that is an important adaptation measure we can do too. Also, site plan review and cluster development. In areas where there is development occurring and people are developing property, it's really important to try and do that in a smart way that has minimal impact on these resources as a climate adaptation measure. So an example of that would just be looking at your site planning and trying to avoid and minimize impacts to wetlands, streams, floodplains on a single piece of property, reconfiguring the dimensions of your project. The same thing if you were doing a larger development. Cluster development allows those natural features to remain intact and continue to provide the functions and values that they do. Okay, I'm going to turn it over to Ralph here.
Okay, everybody hear me okay? Structural best management practices are the same for our climate change. How we apply those for climate change are the same ones we use right now to protect wetlands and streams. And their primary function is to remove pollutants from stormwater runoff by either settling or filtering in some manner. They maintain or restore natural site hydrology, which is one of the most important things with respect to climate change. They prevent erosion and sedimentation, and they maintain the stream or wetland integrity. The BMPs can be applied in such a way to actually maintain shape and habitat. So on the next slide, one of the most important things for, as I said, and what everybody has been referring to, is the hydrology of of runoff from sites that drain into a wetland, particularly with respect to climate change. As we build and change the landscape by adding more impervious surface by either driveways, streets, rooftops, and take away vegetation that took up precipitation and intercepted precipitation even before it fell on the ground, and allowed for water to soak into the ground and get into the groundwater and flow subsurface. That all changes to surface runoff, and the more we transmit that surface runoff, transport that surface runoff via streets and pipes, the faster it gets to waterways and causes issues with both streams and wetlands. The diagram you see is a historic diagram that many of you have probably seen before. With respect to climate change, the changes that we are going, the adaptation of BMPs to protect wetlands have to do primarily with sizing and accommodating different magnitude of precipitation events. So on the next slide, there we go. BMPs to maintain the natural hydrologic cycle. Ann's already talked about cluster development, reducing road size, pervious pavement, green roofs, modular pavement. All of these things reduce the amount of impervious surface. More than anything else, that changes. Nothing changes hydrology more than paving over a area, taking away the any vegetation that was there, and preventing water from infiltrating into the ground. Cluster development, as Ann has already explained, keeps the imperviousness in a more concentrated area and allows the water that does run off to get into green space and natural areas to infiltrate the ground and be taken up by the vegetation. Reduced road size, of course, is the same thing. There's a road down in the middle picture here that is a classic picture from out in Seattle. Minimal roadside size, swales on the side of the road for the runoff that does occur, turnouts and parking spaces a little further up on the road, provide for parking rather than on the road. And all of this reduces the amount of impervious surface and reduces the amount of runoff. Pervious pavement and modular pavement. Modular pavement's on the diagram from the manual up there on the right, and pervious pavement, which is a very similar concept, make the parking lots and roadways that currently are acting as a barrier and as a transport mechanism for water to act more like a meadow and soak up water. Green roofs, same thing. We're transporting or changing a roof from a runoff mechanism to an absorption mechanism. Next slide. A couple simple ways to affect natural hydrology on people's homes is downspout disconnection. That can be a major contributor in some areas where people put their downspouts on the driveways, which is a direct transport into the storm sewer and a direct transport to waterways. Either direct it into green space away from any pavement areas so it has a chance to soak into the ground, or into a rain barrel, which as it fills up with water, then you can use for watering the garden or any other purpose you need water around your property. Next slide. Rain gardens and bioswales are intercept runoff that is generated from impervious surfaces that we can't control other ways, and allow it, in a concentrated way to be able to use the natural mechanisms that were there, plants, deep-rooted native plants that absorb the water, allow it to evapotranspirate. The ground these are either placed in ground that is already amenable to infiltration, or the soils are amended to provide infiltration, or in worst case scenario, very tight soils, through a stone reservoir with underdrains, and take the water that was running directly off of the waterway into and infiltrate and remove a great amount of the vine that came off the site. Next slide. And finally, buffers. There's a lot of different form and function to buffers. I will say that a minimal size buffer for pollutant remover is roughly, or as a pollutant remover is 20 to 25 feet to capture sediment and other pollutants that are running off. The 100-foot wide number you see there is what has been found to be essentially the minimum width to prevent any kind of impairment. Anything less than 100 feet starts to cause different impairments to the watershed, influence on habitat, different species of fish, water pollution, those types of things. So 100-foot wide is what we're shooting for. 20-foot wide minimum by pollutant removal. And from a climate control perspective, it should be a mixture of vegetation that, as the temperatures change and the type of vegetation that can survive the change, the practice will hold up and adapt. Okay, I think Ann?
Nope.
Oh, I'm sorry. Natural shorelines, I almost forgot. Very simple. Just like buffers, natural shorelines are provide habitat features and protection to both streams, wetlands, and lakes. Many practices to protect those features as people build, or as there's other property that is at risk, have been hardened features. Natural shorelines provide the vegetative function that I've already been talking about with other practices, as well as habitat. Vegetation on streams and wetlands also provide a higher level of protection and a longer lasting level of protection. Now, Ann.
Yeah, so as Don mentioned earlier, invasive species are also a significant threat to the health and condition of our coastal wetlands. And in light of climate change, there is significant concern that they will just continue to be more and more of a threat. There might be different ones that we experience, but probably invasive species will continue to be a major issue. So when we're talking about wetland management, wetland creation, and wetland restoration of coastal wetlands, invasive species management is a priority action for really all of those areas. And Don talked a lot about how the onset of very dense Phragmites in our coastal wetlands has really changed the condition and the character of those wetlands and made it harder for them to adapt to changing water levels and to other changes over time. And so that's why invasive species management continues to be a priority action. Also, when we're talking about, especially when we're talking about wetland restoration in and of itself is a climate change adaptation measure. But in particular, when wetland restoration is done in a way that is meant to replace lost functions of a wetland on the landscape, when we're thinking about the potential impacts of climate change, impacts to groundwater and groundwater recharge are a significant threat to our to Michigan in particular. It will significantly impair and change the climate here, as well as could have an impact on agriculture and other things that we enjoy in Michigan, recreation. So wetland restoration, when you target where you locate it on the landscape to areas where wetlands have been lost, and when you use tools like the landscape level wetland assessment, which the state of Michigan has developed, you're able to replace some of those lost functions, in particular things like groundwater recharge. So that is an important adaptation measure we can take too. And then stormwater wetlands. These aren't exactly replacing or restoring wetlands. What we're talking about when we talk about stormwater wetlands are engineered wetlands instead of your typical stormwater detention basin. And they are designed to have certain capacity. They are designed to retain water in some way, but they're not usually just your bowl-shaped open water pond basin with a riser pipe. They often do have native vegetation in them, multiple different kinds of native vegetation. They often have zonation, like a more natural wetland would have. They allow more and faster infiltration of the water into the groundwater. And even though they don't provide the same functions and values as a natural wetland, and they really don't replace a natural wetland, they do provide some of those habitat functions and values that have been lost on the landscape, and they can assist with wildlife corridors and maintaining some wildlife habitat in an area, particularly in urban areas. So engineered stormwater wetlands are also a best management practice that can be utilized particularly in more urban areas. I've mentioned wetland restoration siting using landscape level wetland functional assessment as one of the tools. Another tool that Ralph touched on a little bit is native species planting. Most of the BMPs we've mentioned so far do include some planting, and it does include native planting, but in particular you want to keep in mind planting native species that have a range of hydrologic tolerances. And this is an adaptation measure because there will be wetter years, there will be drier years. Over time, the amount and the seasonality of precipitation we get in Michigan could change. So if you establish a seed bank of native species that have all those hydrologic tolerances, that area, that wetland that you're restoring or managing will be better suited to adapt and to compete with invasive species in light of climate change. So it's important to keep that in mind when you are developing a planting plan for whether it's wetland restoration or if it's for a rain garden, things like that. There is the thought that planting or placing more seed on the land could also be an adaptation measure for these areas. Again, because it could make these areas more competitive against invasive species. And then in particular, when you're planting woody species, there's one of the more progressive ideas is to plant woody species that are near the northern extent of their native range right now, in light of the fact that some of these species may begin migrating north with climate change. Similar to that, when habitat structure development or placement is being planned in wetland management projects, the thought that wetland habitat structures for certain species should be placed at different elevations or zones within your wetland area is a BMP. For example, you might be placing basking logs in the wettest part of your wetland right now, but an adaptation measure would be to also place them in higher, drier areas so that in future years, if we have particularly wet years and the water will be higher in your wetland, there will still be those habitat structures located where the turtles can use them for basking. That's an example of what we're talking about here. So those are basically the best management practices that Ralph and I were planning to talk about today. And if there's any questions, we'd be happy to answer them.
Thank you, Anne and Ralph. We do have a couple questions that came in. I know we're slightly over on time, but we're just going to ask a few, and if you have to drop off, we completely understand. The first question actually is for Ricky, and it is, what is the likely cause of the CO2 emissions in the Great Lakes?
I mean, so I don't know exactly the question. The CO2 emissions that are primarily driving climate change are accounted for by doing a budget calculation and the increase is driven by burning of fossil fuels, and that has a global impact. Most of that CO2 is actually absorbed in the ocean, and then what's not absorbed contributes to the buildup in the atmosphere. There's the potential of other natural or other causes of CO2 emissions that are accelerated by climate change, such as mentioned here, peat and warming of peat bogs in the higher latitudes, and other issues like that. But the primary driver of the climate change and the CO2 emissions is from fossil fuel burning.
Thank you. We have another question. If Don is still with us, or it could go to Anne. What's the relationship between climate change and the invasion of Phragmites? Or does Phragmites require warmer temperature, disturbed sites, low water levels, etc.?
Don, are you there? Are you planning to answer this?
Might have had to drop off.
Okay, real quickly, I will preface this by saying we don't necessarily know the full extent of the relationship between climate change and Phragmites. Certainly, Phragmites and invasive species as a whole are a problem sort of regardless of climate change. They get here typically through vectors. It could be, humans bring them on boats or plant them in gardens, things like that, or it could be that they come here, on crates of shipments, things like that. In the case of Phragmites, it has spread. It's been here for it's been in the United States for a long time, and it has been spreading. It primarily spreads by rhizomes. Phragmites has some characteristics that may make it adapt well to climate change. For instance, it does like areas that have a high salt or nutrient content, and some of our native species do not compete as well in those environments. So with more runoff, with flashier storm events, that could continue to encourage the growth of Phragmites. As for temperature, I don't think that the temperature changes we're anticipating soon will significantly hinder Phragmites or cause it to expand. It's got a pretty broad range of temperature tolerance, so it was here. It's been here for quite a while, and it will just probably continue to be fine. What is more significant is that the water level fluctuations are being disrupted. Like Don was talking about, that 15-year period of long-term low water level, that provided a long time for Phragmites to get a real stronghold in some of our coastal wetlands and really expand. And because it does spread by rhizomes, it has established a very significant root structure in these coastal wetlands now, which just make it particularly virulent. So it's not a direct relationship with climate change, but it's certainly all kind of connected, and some of the things we're expecting with climate change, like significant runoff during storm events, could encourage the growth of those species.
Thank you, Anne. And now we're out of time. So at this point, I'd like to extend my sincere thanks to our presenters and the Office of Great Lakes Coastal Zone Management Program, NOAA, and the DEQ. Thank you, everyone, for attending today's webinar. And if you have any other questions, please feel free to contact either myself, contact information is on the screen, or any of today's presenters. And on behalf of Tip of the Mitt Watershed Council, thank you for joining us, and have a great rest of your day.